We're going to continue working on our quadratic functions review for today. Again, we're on page 17 to start. We're going to look at writing quadratic functions. So we're writing quadratic models based on something. As we talked about before, a lot of times when we're modeling with quadratic functions, we're looking at some kind of projectile. So something is being launched or thrown or hit into the air, and it's going to go up and come back down. So we're going to see a lot of projectiles today. For our first three problems, I want you to note that there's a little note up at the top. It says for problems 1 through 3, use this model equation, this guy right here, where this little v with the 0 next to it, that means v naught. That's our initial velocity, this guy right here. And h with the 0, that's h naught. That's going to be our initial height. So for problems 1, 2, and 3, we're going to use this sort of model and plug in our initial velocity and our initial height that were given in our problem. So for number 1, it says a rocket is launched. We got a projectile. A rocket is launched from the top of a 100-foot cliff with an initial velocity of 116 feet per second. So we're launching from the top of a cliff. That's our initial height at an initial velocity of 116 feet. So we're going to plug these values into our quadratic function here. So our model will be h of x equals negative 16t squared plus 116t plus 100. I plugged in values for the v naught and the h naught. The negative 16 we're seeing in these projectile problems, it's a constant due to gravity. So when something comes up, it's impacted by gravity as when it starts to fall back down. So that's where that negative 16 comes from. So there's our model. B says, what's the height of the rocket after 5 seconds? So we're going to let t be 5, and we're going to plug that into our function. So negative 16 times 5 squared plus 116 times 5 plus 100. This I can simplify on my calculator. So if I pull my calculator over, I would have negative 16 times 5 squared plus 116 times 5 plus 100. I get 280 there. 280 when I simplify. So my question was, what's the height? So 280, I see feet as my height label in my problem. So 280 feet there. Questions for me so far? Okay. For C, when does the rocket reach the ground? So we know that we are launching our rocket from a cliff. It's going to go up and then come back down and eventually hit the ground. What we're looking for here is the x-intercept. Now, we could plug in 0 for our h of x. Our height would be 0 at the x-intercept and solve for t. This is not the easiest equation to solve by something like factoring, or definitely wouldn't want to complete the square on this. We'd kind of be stuck with quadratic formula. Rather than revisit quadratic formula and have to work through all that simplifying, I'm going to go ahead and use a graph to find that x-intercept. Now I'm going to add a graph page, and I'm going to type in the function that we created here. Now, when I type this in, I'm going to use x's instead of t's. Your calculator doesn't know what t means. It's set up for x's, so we're going to use x's. And again, that's the only thing I'm changing about this. Everything else is what we wrote for part A. And now that I've got my graph in here, I see 2 blue lines. That does not look like a parabola. It certainly doesn't look like the sketch that I made. Why does this not look like a parabola? Yeah, my zoom is like super tight towards the origin. So if I want a better picture of this, remember to adjust your zoom. So I'm going to hit menu. I'm going to go down to Windows Zoom, and I like Zoom Fit because it scales the graph to give me a good picture. So here we can see there's the trajectory of our rocket. Now what we want is this x-intercept over here. So I'm going to go to Menu and then Analyze Graph. Remember, for your calculator, x-intercepts are called zeros. Okay? And I click on either side. Don't try to land your dashed line on your x-intercept. Click to one side, click to the other. Now, for this particular problem, I want to point out we're getting this sort of really goofy decimal for our y value. I expect that to just be 0, but it's not here. I fiddled with this problem quite a bit to try to get it to give me 0. What's happening here is I've got negative 1.75 e to the negative 10. So that means 0.90175. Okay, it is a very, very tiny, essentially rounding error on the calculator's part. That e with a negative number there, a pretty large negative number there, is essentially a rounding error for my calculator. We're not going to stress about it for this particular problem. We're just going to take our 8.3 as our x-intercept here. What it really means is that our x-intercept is probably something a little more delicate than 8.03, but our calculator is just having a hard time getting that precision that we want with the float settings that we've got available to us. So we're going to do 8.3 there, that x value. And this would be in seconds. So the rocket reaches the ground after about 8 seconds. For number 2, you and a friend are having a contest to see who could jump the highest. So now you are the projectile. You jump from the ground with an initial velocity of 18 feet per second. So we're going to use, again, that model at the top of our page. And our function would be h of x equals negative 16 t squared. They give me my initial velocity is 18, so 18t. What's my height? What's my initial height? 0. Why is it 0? Yeah, exactly. It's just I'm jumping from the ground. So we can put a plus 0 there since our initial height is 0. It would also be okay if you left the 0 off. And then B says, how high in the air are you after 1 second? So we're going to let t equal 1. This would be negative 16 times 1 squared plus 18 times 1. 1 squared is 1. Negative 16 times 1 is negative 16. And then 18 times 1 is 18. So we would get 2 here. And our label would be feet. And 2 feet off the ground after 1 second. Questions for me so far? For number 3, again, we're going to use that model equation from the top of our paper. Number 3 says a baseball is tossed upwards from an initial height of 4 feet with a velocity of 5 feet per second. Write a quadratic model. So this would be h of x equals negative 16 t squared. My initial velocity is 5, so plus 5t. And my initial height is 4, plus 4. So I let it go 4 feet above the ground. That was the height of the ball when I released it from my toss. B says, when does the ball hit the ground? So again, when we're trying to hit the ground, that means we're looking for the x-intercept. So I'm going to find this x-intercept the same way I found it for number 1. I'm going to go ahead and graph this on my calculator. So I'm going to delete this graph and put in my new function. So negative 16x squared plus 5x plus 4. And I want you to notice that my graph this time isn't great, right? I can't even really see. It looks like it just hits the x-axis. That's because this is still scaled for number 1. So if I want it to not be scaled for number 1 anymore, I've got to go to menu, down to window zoom, and then zoom standard will get us back to the original picture that our default, that our graph defaults to, okay? Now, this time I can actually see that toss. And it's kind of lame, right? It like barely goes in the air and then falls to the ground. But that's okay. All I really care about is what's the x-intercept there. So menu, analyze graph, and I'm looking for that 0. I want to remind you that your calculator will only find one x-intercept at a time. So if I click way over here, it's going to find the first one, and sometimes it will hop to the next one, okay? Sometimes it hops to the next one. It did here. It didn't in my last hour class. So if it doesn't hop to that next one, you got to escape out of here and try it again with your initial click being in between those 2 points. Let's see if it will switch back over again. There we go. So our x-intercept is at 0.68. Got a proper x-intercept that time. So 0.68, okay, for my x-intercept. So we'll glare on the screen before. And again, this is in seconds. So just after half a second, it hits the ground. Questions for me so far? Okay, so we're not going to use that model equation at the top for any of our remaining problems, okay? This was just for 1 through 3, where we had information about an initial velocity and an initial height. If I take a look at number 4, this is also really a projectile problem. This time our projectile is our frog that's hopping along. It says a frog hops on the ground such that it lands 2 seconds after it jumps. It doesn't tell me the frog's initial velocity. It doesn't tell me the frog's initial height, although it does say it jumps from the ground. So I guess I know that information. But without the velocity, that equation at the top of page 17 isn't very helpful. So here's what I'm going to use instead to be able to write my function. I know that my frog hops so that he lands 2 seconds after he started his jump. Excuse me. So I know the x-intercepts for my frog's jump. If I know the x-intercepts, I have all the information I need to be able to write factored form. We have an a value here, we have the x-intercepts, so I can write a function for this. I'm going to use y equals this time. If you want to stick with h of x, that's fine too. This would be negative 16 times x minus 0 times x minus 2. So I can write factored form here instead. Questions for me on number 4? Okay, turn the page for me. Number 5 at the top of page 18, when you dive into a pool, you're below the surface of the water after 2 seconds and resurface after 15 seconds. Write a model. Again, I don't know the velocity of my dive. I don't know if I'm diving from the edge of the pool or from a diving board that's higher up in the air. Maybe I'm already in the water. I don't know any of that information. They did give me my A value, but here's what I can use to be able to write a model. So I'm going to let the surface of the water be my x-axis, okay? Y measuring the depth of my dive here. So at 2 seconds, I go below the water. And at 15 seconds, I resurface. So again, I know my x-intercepts. So this would be y equals 0.5 times x minus 2 times x minus 15. I could sort of think of this dive as like an underwater projectile, but again, I didn't have any information about velocity or initial height. So that standard form function that we use doesn't make sense for what I know about this dive. Instead, I'm using what I know about breaking the surface of the water, treating those as x-intercepts, and I can write a function here. Number 6, again, we have a projectile. We're launching another rocket. Launched into the air and reaches its peak height of 484 feet after 0.5 seconds. So another projectile, but again, I don't know the initial velocity and I also don't know the initial height. So I can't write that standard form equation here. What I do know is the peak of the rocket's travel. So my rocket's going up and coming down, and I know its peak. What point would I call this, or what name would I give this point? That's the what of the parabola? Vertex, yeah. So my vertex is 0.5, 484. If I know the vertex, I can write vertex form. And again, it tells me my A here. So this would be y equals negative 16 times x minus 0.5 squared plus 484. B says find the height of the rocket after 3 seconds. So I'm going to plug in x equals 3 for my function. I would like you to go ahead and type this into your calculator now. Plug in 3 for x and tell me what you get. Would you? Yep, 384. And we're asking about the height. So that would be 384 feet. Good. Questions for me on number 6? Again, I knew a different piece of information, so I picked a different function format for my quadratic here. Our last example for today is number 7. A rectangular field is to be enclosed with 920 meters of fencing. So I've got a rectangle here. The fencing to enclose this field will go around the outside. And in our table, we're looking at the width of our fence versus the area that we're enclosing. So versus this space that we'll have inside of our fence. Write a quadratic model that gives the area of the field as a function of its width. Again, the information I have here doesn't lend itself to standard form, particularly not the model that we use for 1 through 3, right? I'm talking about area. There's no velocity here. There's no initial height. I also don't have y values of 0 in my table, so I can't use x-intercepts on this one either. But what I do see are repeating y values. If I follow those repeating y values to the center, this would be the vertex. So I can write vertex form. So my vertex form would be x minus 50 squared plus 2,500. Now there's one more thing I need to take into account, and that's my lead coefficient. I didn't provide that for you here. So let's take a look at the table so we can make some informed decisions. Now, earlier we talked about how just looking at the table, we can determine if our parabola opens up or down, which means we can determine if that lead coefficient is going to be positive or negative. So if I take a look at my vertex, 2,500, and then I look at the y values right on either side of it, compared to the vertex, are these values lower or higher than the vertex? These are lower than the vertex, right? That means the vertex is up here, and these values on either side are down here. So what we have is a parabola that opens upside down. So what has to be true about our lead coefficient? It's got to be negative, yep. So there's my model function. Now for B, we're going to use our model to figure out the area if the width of our field is 90 meters. So width is our x. We're going to let x be 90. So you can go ahead and plug this into your calculator. Be careful with your signs and your parentheses and your square. So you can simplify that in your calculator and tell me what you get. You got 900. And so this is an area, right? So that would be meters squared. Good. Now for C, same idea, except this time with a width of 10. So negative, in parentheses, 10 minus 50 squared plus 2,500. And tell me what you get. We got 900 again, right? Let's stop for just a second and think about if that makes sense. Would it make sense to have something bigger than the vertex and something smaller than the vertex have the same area? Potentially, right? I've got that here with 40 and 60 and with 70 and 30. If I take a look here, 90 minus 50 is 40. So this would be 40 units bigger than the vertex. 10 minus 50 is negative 40. So this would be 40 units smaller than our width for the vertex. Since parabolas are symmetric, whatever I get here should be the same as whatever I get here, since they're the same distance from the vertex. This is essentially the same rectangle. For one of them, it looks like this. For the other one, it looks like this. Okay, based on what I decide to call the width. Questions for me for today? Okay, I want you to use your remaining class time to continue working on your delta math assignment over your quadratic.